All right, so hello everybody, and thank you for coming to my talk here. This is going to be on how we can get better use of SQL for FHIR, is the title of it in the book, which is true, but a lot of it is also going to be about the data platform that we've been building within Google for dealing with FHIR data. We've been developing it for our use for research and development, but we think it can be really useful to a lot more broader applications. So we've been making it open source at github.com/google/FHIR. Feel free to take a look. If you happen to be at Amsterdam in last November, we gave a talk similar to this one. This one's going to be a little bit more focused directly on SQL analytics, but a lot of it is going to be covering similar grounds. I want to make one point, which is both of those talks we were describing this, both that talk and this talk, we have not yet come out with our 1.0 release. We're really hoping that that will be coming very soon, and that by the next time we give this talk, we're going to be able to describe this not as something that you should be paying attention about and thinking about, but that's something we really want you to try out and start using. So, as I said, everything I'm going to discuss here is open source, free use, available here. It uses the Bazel build system, which if you're not familiar with, it's just a really easy way to define targets and dependencies and make your life a little bit easier. All the documentation is on there. I'm not going to go into details on that. One other thing is a lot of the code you're going to see here is going to be using STU3. We've actually just finished putting out an R4 release, but it's not up on the GitHub yet. That's probably going to come literally later on today. So if you look tomorrow, R4 might be there, but it's not there quite yet. The last link I'm putting here in the FHIR is the FHIR/examples, and that's where you're going to find a lot of usage examples. A lot of things that we're going to be discussing in this talk. There's readmes, and you can do them in code that you can run and get to play around with this stuff today if you want. So I'm also not going to go, so a lot of the analytics we're going to talk about here are on BigQuery. How many of y'all are familiar with BigQuery? Is that something that, yeah, it's a decent amount, great. So I'm not going to go into a ton of detail other than to really briefly say it's a queryable database you can upload, it's a data warehouse. So you go ahead and give it a schema for your data and give it some JSON, and you can run SQL queries against it. And that's what we're going to be using for a lot of the examples here. So, okay, you're uploading JSON. FHIR is JSON, so this should be easy, right? It's not quite that easy. If you're familiar with your FHIR spec, you know that FHIR doesn't really lend itself very well to a schema. Take a real simple example. Everything can have contained resource that can be any kind of resource. So theoretically, your FHIR schema can expand infinitely. The same applies to extensions. So I'm not going to go into a huge amount of detail on this right now, other than to say we have tooling that can take the structure definition for a resource, generate a BigQuery schema for it, and it'll prune some of these harder parts of the schema and let you get something that'll work. And similarly, we can take FHIR JSON, we can pass it through a formatter and get analytic JSON out. Don't take this slide too literally, because we first go through a layer of proto, which we're going to talk about later. The bottom line is, if this were the whole story, this would be a very short talk, because you can do a lot of really cool stuff with this, and here's a link to an example to play around with exactly this kind of stuff. You can get some Cynthia data uploaded into a BigQuery instance, and you can query it. And BigQuery is nice. You know, you can query nested fields. You can do a lot of things with flattening repeated fields, so that you can query in a lot of ways that are otherwise very difficult. I'm not going to go into a lot of detail about that. Again, if you're interested, there's a lot of information online about working with BigQuery and Google SQL. So here's a really simple example of the kind of query you can run on Cynthia data. What we're doing here is we're saying, give me the top conditions sliced by gender. And because everything is well typed, this all comes out nicely. We can go look at nested fields like condition.subject.patient_ID, and you can get results. But that's an easy one, and things get hard quickly. And why do things get hard quickly? Consider this as a query. Give me all the observations that have either a given LOINC code or a given SNOMED code. Conceptually, it's pretty straightforward. Seems like something you ought to be able to do. But this turns out to be very difficult. And the reason is because there's no field for LOINC code on observation. There's no field for SNOMED code. Instead, what you have is CodeableConcepts. And if you're familiar with your FHIR spec, those are very difficult to query because it's basically an unstructured key value pair. We're going to talk a lot more about this example. Here's another one that's a hard query. Give me the top condition code sliced by US core race. So this is very similar to the one we just did by gender, but because race is not a field, it's an extension, it's a lot harder. So that's the motivation for this talk, is we feel that by using protos, we can take these queries that are otherwise very difficult and make them very easy. So that's going to be the motivation for this talk. So I'm going to break the rest of this talk into roughly 4 parts. What are protocol buffers? Here's another one. How many people here are familiar with a protocol buffer? Great, awesome. So I'm going to be talking a little bit about that, but I'm not going to spend a ton of time because you can probably guess a lot of it. The second is how have we made FHIR fit into protocol buffers? Third is how can we use profiles to make SQL analytics easier and more powerful? And finally, how can we generate custom profiles that match your data? So starting off with what are protocol buffers? My 1-sentence line is that protocol buffers are a type-agnostic way of defining type-safe, space-efficient data structures. Did I say type-agnostic? I mean language-agnostic. So we're going to go through all of those points in turn. So here's an example of a definition of a protocol buffer for person. This is not a FHIR person. This is just a very generic thing. It looks like a struct in IDL. It's just a simple way of defining a data structure. We've got some primitives up at the top, like string and integer. We've got a custom enum that we've defined, and then used in a custom data, or in a nested substructure. And finally, at the bottom, we have type defined elsewhere, which is just referring to some message that's been defined elsewhere. It's pretty similar to any kind of other struct you might have defined in your programming career. One thing I want to key on is this =1, =2, =3 syntax. If you're not familiar with protocol buffers, that might look strange. What we're not doing, we're not like assigning any value. What we're doing is we're giving each field a tag number. And the reason this is so powerful is that assigning each field a tag number means that when we serialize this data to disk, instead of having to do like JSON where you have a string that you're storing as a key, instead all you have is this tag number. This means you can efficiently serialize and deserialize these protos to disk and get a huge byte size reduction. These messages are then taken and compiled into code. When I say that it's language agnostic and type safe, what I mean is you get these accessors, setters, and getters. This example is Java here, where you see that all of those fields get turned into well-typed messages, well-typed functions on the data. And type agnostic or language agnostic because there's implementations of Proto provided by Google for just about any language you can imagine wanting to work with. Here's a subset of them. See if you can pick out which is which. But this is a tiny subset of all the languages that Proto will work with. And this means you can take a message from a C++ server, pass it to a Java server, pass it to a front end, and it'll be the same message definition all the way through. So they can be serialized, they're compatible across language, and they can be sent over the wire or saved to disk. So inside Google, protos are what we use for absolutely everything. Every single project from the biggest to the smallest uses protocol buffers as their backing, so there's never really any question about what we were going to use to store our FHIR data. A lot of internal tooling just works naturally with it. A lot of the SQL queries, we don't even need to go through BigQuery because we can query them directly. We can debug, view data, reflection in multiple languages, etc. So much so that the running joke in Google is that the basic job of a software engineer at Google is to move protos from one place to another, and all of Google is just one giant proto moving company. So okay, so that's what a protocol buffer is. Now let's talk about what does FHIR look like when we're representing it as protocol buffers. Here's a simple example. On the right, you see the structure definition as you'll find it on the website. On the left, you'll see it as a proto. All of these are primitive or data types that are defined elsewhere, but you can see pretty much it's a one-to-one correspondence. You can look at how those data types are defined to get a better idea, but the basic idea is it looks like you would expect it to. There's not a ton of surprises. So what's our approach to actually getting these? The big one is we auto-generate these proto files from structure definitions themselves. What this means is that we haven't sat there and hard-coded every single resource for a lot of reasons. One, it would be an incredible pain to do, and another, it would be incredibly hard to modify to new versions of FHIR, add new capabilities, or anything like that, because there's just so many of these resources. So by tying it directly to the structure definition and auto code generating these proto files, we get the ability to stay very, very tightly coupled with the spec at all times. We never deviate from the spec, and we can continue to add functionality to it. Internally, we use protobufs for everything, but we keep FHIR JSON for external connections. This means that at any point we can freely move back and forth between protos and JSON, and it's totally lossless, it's totally spec compliant, and this is what, if you look on the FHIR website, they talk about JSON, XML, and Turtle as the accepted FHIR formats. We really think about proto as another one because it's totally isomorphic, it's totally easy to move back and forth between them. So this is a point that I'm going to stress a couple of times through the talk, is even though we've made a very different and type safe and all of this representation, at all times, everything we do, even as these protos are going to get more complicated, it's always freely moves back and forth between all other FHIR formats. We're going to try to enforce constraints at both compile time and runtime. What this means is that, sure.
So for internal purposes, can we still work with protobufs rather than going with JSON?
Absolutely, and this is kind of the second facet to this talk, that in this one I'm going to be talking a lot about data analytics, but I want you to keep in mind this programmatic access to protocol buffers, which we use all the time internally. We do a lot of very complicated things with it. We turn them into sequence examples for machine learning. We do a lot of serving and things like that. All of these are just a whole lot easier when you have programmatic type-safe access as opposed to treating them as JSON. So internally, we always use them as protos. And when I say we can enforce these constraints both at compile time and runtime, what I mean by the compile time there is you have a type safe because you're using getters and setters. You're not just saying, like, get me this random field out of JSON. You're saying, get me this email, which you know is a string, et cetera, et cetera, et cetera. And then at runtime, we can validate FHIR constraints and FHIR path constraints. We're going to make the protocol buffer do as much work as possible. By this I mean when we parse the data from FHIR JSON into protocols, we want to do as much of the heavy lifting during that point as possible so that by the time you have it in protocol form, it's as easy to work with as possible. So to take bear with me here because this is going to be a really complicated diagram I'm going to do here. This is how our proto generator works. So we start off, we take a bundle of JSON structure definitions as defined by FHIR. We pass them to the proto generator, and we get proto files out. So the key here is that there's no manual work, there's no, it's entirely generated and it's entirely coupled to the spec. So I want to talk a little bit about the primitive types. I'm not going to go into a ton of detail because a lot of this is on you can see in the GitHub. But when I say that we do as much work as possible in the parser, I want to talk, for instance, about date time. If you're familiar with your spec, you know that date time is represented in JSON as a string, which means that all of the information like time zone and being able to put this on a timeline is difficult without parsing. So instead of having to parse that string every time you want to use a date time, we're going to do that all in the parse step because we're going to have our date time primitive, quote unquote, that actually has a lot of data on it itself. We're going to turn it into a value in microseconds, a unique epoch, and we're going to parse out that time zone. So anytime you use this in the future, you have direct access to the useful bits instead of just having access to a string. Last thing I want to point out is down at the bottom. On our primitive type, we define string ID and repeated extensions. This means that anything you can do in the FHIR spec, you can represent in the proto form because you can add ID and extensions in whatever other fields are required by the spec itself. And this is true for even the simplest of types like Boolean, which is basically just defined as a bool and ID and extensions. So FHIR JSON fields are not one-to-one with protocol buffer fields, as you see here. It's not just an exact correspondence. This means you need custom libraries to get your data between JSON and proto. We provide these. We've open sourced them in Java and C++, and Python and Go are going to be coming shortly. The Go one is pretty much all there. We just need to open source it. And this allows us to fluidly move between FHIR JSON and proto JSON at any time. So another big part of our approach is inlining codes as enums. And this makes it impossible to have invalid code. This is going to be a repeating theme that we're going to get to throughout this talk, especially once we start talking about profiles, is we want to make it as impossible as we can to input invalid data. So, for example, let's take a look back at our patient resource. You see that if you look at the spec on the right here, we see that gender is defined as a code. And if you're familiar with your FHIR spec, you know that code is basically a fancy word for string, because in the JSON itself, it's stored as a string. But there's a little bit more to it than that, because it has a strict binding, it has a required binding that says that this code has to come from this code system. And so the way we handle that is we take that field, and instead of inlining it as a string or just an arbitrary code, we inline it as a enum for administrative gender code, which we can also go ahead and read the value sets, the code systems, and we can generate a well-typed enum. This means it is literally impossible to input bad codes into your spec. And this is just an easy way to reduce a lot of errors. So let's take a look at a quick example. Here's our patient Fake Dudington, who represented here with pure FHIR JSON and represented here as a proto. So a couple of things I want to point here is look, for instance, at the number of strings that have to get stored. On the left, basically everything is a string. And on the right, the only things that are stored as strings are the actual strings. All of these things you see, like ID and value, we go back to that tag number where you use the tag number to serialize it. So you get an enormous byte size reduction. Just right here, you get like a 10-fold byte size reduction at least in terms of how much you have to store on disk by using proto. So in addition to being type safe, in addition to being easy to use programmatically, it's also a huge byte size reduction. And you get this direct programmatic access. So, and again, I want to stress that no matter how fancy we get, it's always going to be isomorphic with FHIR JSON, and I guess also XML, although we don't really use that. So, okay, so that's how we're representing FHIR as protocol buffers. The next question is, how can we get fancier and do things that are hard to do by making use of profiles? So let's take a look at that example we were looking at earlier. The reason this example is so easy to use in BigQuery on FHIR proto data is that everything is a field. So subject.patient ID is a field, gender is a field, code.text is a field. These are all well-defined top-level fields in the resource itself. But some fields are really hard to work with. So let's talk about a couple of examples of that. FHIR gets a lot of its flexibility through key value pair fields. These are things like extensions and CodeableConcepts are the two big ones we're going to talk about. And these fields are very hard to query because instead of being well-structured data, they're key value pairs. And I want to stress that every serious analytical application of FHIR is going to be using these a lot. So it's not like this is a corner case. This is going to be a core part of how we interact with FHIR data. So let's take a look at extension as a great example. So here's our spec, how the spec defines extension. It's got a URL and a value. The URL kind of points to where the description of this extension is and what it looks like, and the value is what the value is itself. Now that's all well and good, and if that were the whole story, it would be not too bad, but as we all know, that's not the whole story, because it can also potentially have extensions. So because an extension can have extensions, which can have extensions, which can have extensions, you can encode arbitrarily complex data in a single extension. And this makes it a real pain to work with. It's really, really, really easy to get these wrong if you have untyped data, because you're just counting on every user to get that right. And not only is it easy to get wrong, it's hard to query. Let's say we want to select all patients where there exists an extension with birthplace where the city is San Francisco. Think for a sec how you would write that query. You can do it. It's doable because Google SQL lets you flatten fields so you can, kind of treat every extension as its own record. The point is, a very simple query where birthplace is San Francisco all of a sudden becomes really hard because this is an extension. How about this one? Get me the top 2 mothers' maiden names by city of birth. Both of these are extensions. Now all of a sudden this becomes extremely difficult. And we're going to come back to this example. It's a very similar sounding query to give me the top 2 conditions sliced by gender, but because these are extensions instead of top level fields, it's really hard. Another example is CodeableConcepts. So if you know your spec, a CodeableConcept is basically a repeated coding, where each repeated coding is a system and a code. So basically, you have a list of key value pairs that describe whatever concept you're trying to describe. So let's give an example. Give me all the observations from that have either this LOINC code or this SNOMED code. This is a really hard query, and I wanted to emphasize just how hard this query is. So I got our analyst, Gabby. She's a brilliant analyst. She can definitely do it. This is what it looks like. So it is possible, but a very, very simple sounding query is devilishly difficult because it's dealing with this unstructured data. So working with unstructured data is really hard, is the problem we want to solve. And our key insight here is that profiles give us a map of what unstructured data looks like. I like to think of FHIR resources as this kind of like really, really nice apartment where everything has it's someone that cares a lot about everything being in its right place. They've got the bookshelf, they've got the history books on one shelf, they've got the novels on another shelf, they've got a well-placed kitchen where everything in its right place. But then there's everything that doesn't have a place. And everything that doesn't have a place just gets kind of dumped into a big pile in the corner. And that's what extensions in CodeableConcepts are, because there's no well-defined structure. So our key insight is that profiles tell us a lot of information about unstructured or semi-structured data, what extensions to expect, what code systems to expect, and we can treat these like an IKEA manual for building a new bookcase that we can add, and we can take all of that stuff, all that crap that's dumped into the pile, and we can put it in this new bookcase we've built, and now all of a sudden you have well-defined fields for querying. So we can use these profiles to generate even more structured protos. If you're familiar with your FHIR spec, you know that a profile is really just another structure definition. And if you look at the snapshot of a profile, you get the full information you need to understand that resource. And a profile is basically just a subset of the thing it's based on. So for example here, our US core patient is a subset of patient. Basically anything that's a valid US core patient is a valid patient. Now this might sound a little bit funny because if you're familiar with profiles, you know that they can add new fields. Things like US core race, US core ethnicity, and these kind of seem like constraints on what you can have or new things that you can have. But the key is that things like, for instance, in the base patient, you can have 0 to star names. But in the core patient, you have exactly 1. This tells us a lot of new information. Oh, I guess you have at least 1, sorry. For things like gender, you have exactly 1. And then for things like US core ethnicity, this tells us here is an extension that you can expect. It says you can expect there to be a US core race. We don't know that there will be because it's 0 to 1, but this is something that you should be thinking about. So our key insight is we're going to use that to construct a top level field that we can use for this information. So here it goes back to my very complicated diagram. And the key here is that profiles are also structure definitions. So all we have to do to make this work with profiles is to feed it profiles and then have code within the generator that knows how to handle slicings, to take slicings and turn them into top level fields. So let's take a look at examples. So this is our US core ethnicity extension. It is an extension that defines sub-extensions. So instead of having a value itself, it has 3 sub-extensions with known names and known types. So this is a profile on extension. We can feed it to our proto generator and get back a proto. This is the proto you get back. It looks pretty much how you expect. It's got codings, it's got an ethnicity text. All the fields that you just saw get turned into fields on the proto. Next, let's take a look at the US Core Patient Profile. The US Core Patient Profile defines a slice on extension for ethnicity. This is how they signal to us that you should expect there to potentially be an ethnicity extension. It's going to have the slice name ethnicity, and we're going to have this, the URL for it is going to be defined by this profile here. We can take that information when we're generating the proto and hoist that extension up from in the extension pile onto the bookcase. So this is where we now all of a sudden say there is now a field in our US Core Patient that we're going to generate for ethnicity, and it's going to have as its message type that message that we defined earlier for it. So now that's all well and good, but if you have to fill that out manually, that's not really helpful for you. So we have these libraries available where you can take a patient in whatever form it came in and turn it and profile it into the well-typed version of it. So in this case, we have a patient resource. So you can read, for instance, there's a library to take a raw JSON, read that raw JSON into a patient resource, then take that patient resource and convert it into US Core Patient, and with 2 lines of code and no logic whatsoever, you now have access to all of these top-level fields. We have this open sourced in C++ with Java, Python, and Go are going to be hopefully coming as soon as possible. So just to take a look at what this looks like in the data representation, here's the unprofiled patient with extension just as a key value pair in the pile. You pass this through our profiler, and out pops the OMB category neatly filed into its place in our new cabinet that we've built inside the profiled version. And now you also get all these same benefits we've been talking all along about, patient.getEthnicity, get OMB category, et cetera, et cetera, et cetera. So, and once again, I want to be clear on this point that you can take these profiled protos and serialize and deserialize back and forth between FHIR JSON, and it's going to unpack all of these back into extensions and give you totally valid FHIR JSON at all points. So now, all of a sudden, that query that was so difficult before is really trivial now, because we've taken that field, we've organized it, we've hoisted it, and now you can get direct querying access to extensions because you gave us a profile that describes what extensions we should care about. We can do a similar thing with coding to inline codings within a CodeableConcepts. So for instance, here's an unprofiled observation where we have, remember we were talking about these different systems. So for instance, in this case, we have a system for LOINC, and we have some kind of harmonized system that you might use internally when you want something nicer than LOINC. And we can, if you define in your profile slicings that are, we expect there to be a LOINC code and we expect there to be a harmonized code on our observation, we can build a nice little bookcase for that, file that data on there. And now, remember this query that I showed you before was incredibly awful, right? And the reason it was incredibly awful is because there isn't this bookcase. Because we've now well organized this data into queryable fields, you can take this query and turn it into this query, which is pretty much like if you had an ideal world, how would you want to look at this data? This is what it would look like. So that's all well and good if you have these profiles. And if you've been to some of the FHIR talks, maybe you've seen some other ways to generate profiles. We have our own that goes entirely through Proto, and it's designed to integrate very nicely with the rest of our system. So I'm going to talk a little bit about that. So we make it. We want to provide a simple, unified, end-to-end process for looking at your data, identifying what extensions you care about, generating protos, converting the data, putting it up on BigQuery, and making it instantly searchable. So we're going to go back to our diagram, and we're going to add one new step to this. Now it's going to look like this, where we're going to, instead of starting with the profiles, we're going to start with what we call a profile config. You can find this and information on it on the GitHub. I'm not going to go into too much detail other than to say that it describes a delta. All you have to describe is the delta. This can be something like adding a new extension, profiling a codable concept, changing the size of a field as long as you're restricting it. Anything that you would want to do in a profile, we let you describe as a delta. You feed that along with the base structure definition into the profile generator, and you're going to get out a bundle of profile structure definitions. You're going to feed them to the proto generator, and you're going to generate a proto file. This looks like a lot of steps, but we define Bazel build rules. If you're familiar with Bazel, you know that you can define custom build rules so that basically all of this is done with, 10 to 15 lines of not code, of just defining your dependencies, defining your input files, and it'll go ahead and do all of these steps for you, and out will pop neatly structured profiled structure definitions along with the protos themselves. So you also get, so you not just get the well-structured protos, you also get the structure definitions themselves. So this makes it easily shareable and interoperable with any other system that expects profiled data in. So the example I'm going to talk about here is available here. I encourage you to take a look if you want to play around and do this yourself, or run it on your own and mess around with querying it. But the basic idea is I'm going to go back to this other hard question we talked about. Give me the top mother's maiden names sliced by birth city. These are both extensions, and they're not in use by any existing profile. So let's say you wanted to run this query. You got to do a little bit of legwork first. But I'm going to hope to demonstrate that it's not that much. This is the entire profile config that you would need to generate that. I'm hoping that it makes a lot of sense without going into too great detail. So we start off, we say the name of this thing is demo patient. We give it a little description, and we provide a base URL. This means this allows us to do like, proto inheritance basically, structure definition inheritance. We say that start off with the US core patient. So once you have the US core patient, you're going to go ahead and provide deltas on top of that. How does this differ from the US core patient? And it's going to differ in two ways. It's going to have an extension slice for mother's maiden name for all data that has this, for all extensions that has this URL, and it's got an extension slice for birthplace for all things that have this URL. And out pops what you would expect. We look at the, since mother's maiden name is an extension for type string, we skip over this whole generated data type and instead inline it directly as a string field. Similar for birthplace, we inline it directly as an address field because that's what the extension profile tells us to do. And all of a sudden, that query becomes trivially easy. And again, I want to stress that you don't have to write any, it's not just that we're generating the proto, it's also that in the libraries provided by the GitHub platform, provided by our data platform, it'll automatically take data that is unprofiled and convert it into this profile. So basically you need 2 lines of code. Load the data, convert, I guess 3 lines. Load the data, convert the data, upload the data. And that's, once you've defined your own custom profiles, that's all. And it'll work on any profiles out there, and you can make your own profiles using this proto config. I cheated a little bit for this slide if you're paying close attention. I do substring O2 of mother's maiden name because the Cynthia data set that we have is not enormous and there aren't a ton of collisions. So if you're wondering why I did that. And once again, no matter how much you profile this, no matter how much you restructure this, we can always pop back. I'm going to hold questions to the end. Thanks. We can always pop back to JSON. I'm almost done. So that's more or less the theory here. I want to go over the takeaways a little bit here. The proto implementation of FHIR can be useful to anyone that needs analytic or programmatic access to FHIR data. So most of this talk has been about the analytics section of this. Within Google itself, for our research and development, it wouldn't be possible without this kind of like direct programmatic access. So the main motivator here has been about why FHIR protos help with data analysis, but if your purpose is more about doing difficult logic on protos, it can be incredibly helpful to all of a sudden go to a well-structured, well-typed data format. We currently support approximately 3 levels of use. You can think of it as, if all you care about is using the core FHIR protos, if all you care about is taking data in the core FHIR format and being able to use it programmatically, being able to query against it, that's really easy using the existing protos. You can parse data into it and get access to it. You can use it with the existing profiles and extensions. These are things like US Core, things like profiles defined by FHIR itself, things like BMI observations, blood pressure observations. These are all profiles defined as a part of the core FHIR spec. So you'll get those benefits. Also US Core, also QI. QI is a big one, and I'm hoping to talk more about that in the coming weeks or so, is that we really are very excited about supporting the QI core as a part of our spec, which means that without doing any work out of the box, you can put your data into the QI profiles and run analysis on that. That's the kinds of analysis that every hospital in the country has to do. And finally is the ability to generate profiles and extensions that custom fit your data needs. If you've worked a lot with FHIR, you've probably defined extensions, because it just isn't the case that everything you need to do fits neatly into existing fields. And even if you don't need new extensions, you're almost certainly going to use CodeableConcepts, right? So that's perhaps even the more common one, is everything in FHIR uses CodeableConcepts, and they're a total pain unless you know exactly what systems they're going to be, and then there's no reason for it to be difficult. That's at least our theory on it. By using the core FHIR protos, you get type-safe programmatic access to fields and codes, you get validation, you get cross-language support, you get an enormous byte size reduction, you get standard compliant reading and writing of FHIR JSON, and you get analytic JSON for querying through things like BigQuery. Using the profiled protos, you get validation and querying of expected extensions. This makes it impossible to, for instance, have a poorly formatted extension where you've accidentally flattened a field or accidentally expanded or whatever. It's impossible because it's programmatic. You get validation and querying of expected codings. You get type-safe programmatic access to extensions as first-class fields on resources. And finally, if you go ahead and generate your own protos, you can define your own extensions, define what codings to expect, and get these all hoisted up as top-level fields while still being totally interoperable with any other FHIR system. One more time, here's a link. You can't click on these, unfortunately, because you don't have the slides. But if you go to this, the GitHub URL, these are the subpaths to these things, and they all have readmes, especially if you look at, I would suggest starting at the usage examples that have readmes that have good instructions for a lot of these things. For instance, the two that we talked about here, we're taking data and getting it into BigQuery as just basic protos, and a version of it using profiles. So that's my talk. Thanks for coming, and I'll open it up to any questions.
So my question is, when you're creating custom extensions, you mentioned that as long as you create the profile and you use the profile config file, that would generate the required protobufs. And you showed the proto-generated.java. So for these custom extensions and profiles, do we need to modify or extend that Java class, or we can use it as is?
Nope. One thing to be aware of with protos is that they don't actually directly support inheritance. So we don't, for instance, there's no literal inheritance in code between, for instance, US Core patient and patient. But every profile has 100% of the information needed to generate it, other than things it references externally, for instance, extensions. So, and another distinction I want to make is that the profile config itself doesn't generate the proto. The profile config generates the profile, which is structure definition, which then generates the proto. And the reason why I think that's an important distinction is that there's no distinction between a proto that was generated by a profile config versus one that comes from anywhere else. So you can freely interoperate between, for instance, the US Core and things that you've generated yourself.
Your example with the mother's maiden name, so lifting the extension up to a top-level element, does that happen no matter where that extension occurs inside the profiled resource?
It will be lifted to the thing that is an extension on. Right. So if you have a backbone element that's 10 levels deep, and it has an extension on it that you've profiled, it'll be lifted to that backbone element.
Right, so just into that context.
Yep, exactly. It just takes it from an extension field and moves it to a field on that thing itself. We had one over there somewhere.
Two related bundles and contained resources.
You can get the microphone, sorry. Thanks.
Two probably related questions, but bundles and contained resources, are they handled within the base protos or?
Yeah, so a contained resource is inlined as a data type that we generate called contained resource that is basically a one of all possible data. So it will be, and there are options about how you can do this, and we do it in both ways. We have what's called, I forget what we call it actually, but there's sometimes, for instance, it's very common when we do it ourselves to take medication requests, for instance, and add the medication itself as a contained resource, but you don't have to. You can also keep it as an internal reference to other places within the bundle. So bottom line is just like JSON, you can do it either way.
Okay. Any big gotchas?
Any big what?
Any big gotchas or completely lossless? Or?
Oh boy. Yes, between the FHIR, between our proto and the JSON, it's completely lossless. If you go to the analytic JSON, it's not completely lossless, but it's a well-defined schema there. It's not meant to be a representation of FHIR. It's meant to be a version for querying.
I think we're out of time, but maybe a final question. Will you be available for meet and code in the lunch, for example?
Sure. Yeah, absolutely.
Great. So in the McKinley room. Thank you.
All right. Thank you very much.